So in this video, I'm going to explain about the next logical instruction, which is called ORI. So the meaning of this instruction is logically or immediate. It means it will perform here logical or operation with the content of accumulator and as a operand 8 bit of immediate data here. So for this instruction, their opcode will be ORI and their operand will be 8-bit data. So now we can understand this instruction with the example. For example, let's say we are writing here ORI 85H. So here just assume that before execution of this instruction, I am taking here as a accumulator content as a B7H, and here this data we had taken as a 85H. Now we will see their operation here. So this accumulator accumulator content is taken here as a B7H, and this data it has taken here as a 85H. So B means it will be taken here as a 11. So B means 11, it means it will be 1011, and 7 means it can be written in the binary pattern as a 0111, and this 85 means it will be 1 000 will be 8, and for the 50101. So now we need to perform their logical ORing operation. So as like previously also had explained about this logical OR operation, if there is any 1 in the input, then their output will be 1. If both the inputs are 0, then their output will be 0. So from the first stage, any one or both can be 1. So here from the first stage, their output will be here as a 1. From the second stage, 1 ORing with 0, it will be 1. From third stage, 1 ORing with 1, it will be 1. From the fourth stage, both the inputs are 0, so their output will be 0. From the fifth stage, it will be 1. From the sixth stage also it will be 1. From the seventh stage, both the inputs are 0, so this will be 0. From the eighth stage, which is called the last stage, so both the inputs are 1, so here also it will be output 1. So now we got it here 1011. It means it is giving what? 1011 means it is here their hex equivalent will be B. For this one it will be B, and for this one it will be 7. So here after performing this ORing operation, the result will be stored into the accumulator. So that will be having here as a B7H. So after execution of this instruction, the content of accumulator will be changed as a B7H only. Whatever is the result obtained here, so that will be stored into this one. So that is coming here as a B7H. It means B7H will be stored or it will be replaced with this accumulator content here. And now as like whatever I had explained for ORA, the impact of this operation over the flag registers will be also in the similar fashion. So here sign 0 parity will change as per the result obtained here, and auxiliary carry and carry will be reset always irrespective of the result here. So sign flag, it is here giving 1, so it means that the MSB of this result is 1, so their sign flag will be 1 here, and the result is non-zero, so here this 0 flag will be 0 itself. And if you count number of ones here in this result, so here it is saying 6 number of ones, so 6 means it is here even number, so parity bit will be 1 here, and auxiliary carry will be reset, as well as this carry flag will be also reset. So this is the impact over the flags after execution of this instruction. So here in the note we can make this, that sign 0 parity flag will modify to reflect the result of operation. And as like this ORA here also, this auxiliary carry and carry will be reset. Auxiliary carry and carry flag will be reset. The reason behind that, with this one, whatever is the logical operation perform, even from this fourth stage, no extra bit as auxiliary carry can be generated, and from the eighth stage also no extra bit as a carry can be generated. So that is the reason, as per their design aspect, they had taken this auxiliary carry as a 0 and carry is also 0. It means both the flag auxiliary carry and carry will be reset here. So this is the key point here you must have to remember while applying this instruction into the practice. So here now we will talk about their size. So as like we had seen in this instruction, what it has given, ORI 85H. So this 85H is the data and this ORI is the opcode. So here, to store into the memory before execution of this instruction, first of all it will store their opcode hex equivalent for this ORI. So that will take 1 byte, and in the very next byte it is going to store this 8 bit of immediate data as a 85H. So let's say, for example, if I am assuming here for this memory address, if I am taking here 2000H, so here as a data what it will be storing, first will be opcode for this ORI. So let's say their opcode is F6H, so that will be stored at this location, and at the very next location that will be 2001H. So at this place it is going to store this data as a operand, so that I had taken here as a 85H. So this will be stored inside the memory before execution of this instruction. So whenever we will press execute button into that processor kit, then microprocessor will start to read the data from the memory chip. So first of all it will read this opcode, and this is called the first machine cycle, and then as a second operation, like during the execution of this instruction, microprocessor is knowing that their second operand is outside of the processor, which is stored in the memory at this location as a 2001H. So from here it will take this 85H. So before execution of this instruction, it is going to occupy two memory location. Each is the size of word size is 8 bit here. So as a size it will take 2 byte. As a size it will take 2 byte. And as a machine cycle, what it will take? First one is called here as a opcode fetch. This one is called here as a opcode fetch. And second one is called as a memory read. So this instruction will take two machine cycle. First one is called as a opcode fetch and second one is called as a memory read. So here by that way it is going to complete this. So as we know that by default for this opcode fetch it is required 4 T state, and for the memory read it is taking further 3 T states. So total number of T states required for the execution of this instruction will be 4 plus 3, which is called here as a 7 T states. So I hope you have much of clarity for this instruction operation and what is their size and how we are finding their machine cycle T states. So these all the things are clarified with much of clarity of their operation as well as their flag impacts. So I hope you understand this instruction in the better way. Thank you. So now before going to the next logical instruction, here itself I would like to summarize about the flags impact over the first 6 logical instructions. So here the first one we had seen, that is called ANA, and we had seen ANI. So for these two instructions, that sign 0 parity will modify to reflect the result of operations. But this auxiliary carry and carry, how it will be here? So auxiliary carry will be set here and this carry flag will be reset here. So this is the main important point here. Now for the next two, that is called XRA and XRI. So that is called logical XOR operation. So here also for this instruction also sign 0 parity flag will modify to reflect the result of operations, but auxiliary carry and carry, this both the flags will be always reset irrespective of the result obtained after the operation of this XOR operation. So next one is that is called ORing. So ORA, that is called logical ORing, and ORI. So for this instruction also sign 0 parity flag will modify to reflect the result of operation, but auxiliary carry and carry, this both will be reset here. So now this will help you to use these instructions and what is their impact over the flags while solving the problems or giving the exam or using this instruction for the many more purpose. So here this table, if you like remember in your mind, then it will be very helpful to track this instruction in further for the utilization. I hope this will be very helpful to your preparation. Thank you.